Welcome back to Approximation and Stability, and in particular to Chapter 4. In Chapter 3 we learned a lot about approximation methods, in particular projection methods, different classes, and some positive results about applicability. In all these ideas, the assumption was that our operator A is invertible. Now we will have to go away from that, because sometimes it's not invertible. What do you do then? This is one of the main questions in Chapter 4, and you can see it in the headline already that we replace AX equals B by AX approximately equals B, which means we deal with least squares problems instead of equalities. Another question that we will deal with in Chapter 4 is, what if my sequence AN is not stable? Okay, that could have different reasons. It could be a problem with invertibility, or it could be a problem with drawing inverses, or both could be wrong. We will see and we will learn how to deal with that. One of the key words here is regularization, and you will see what about that. Remember from the first week of this course that solving least squares problem has to do with the Moore-Penrose pseudoinverse. So our first subsection here is about a little recall of properties of the Moore-Penrose pseudoinverse. And the motivation was to solve the equation AX equals B as good as possible when A is not invertible. And of course there could be two reasons for non-invertibility. It could be the case that A is not surjective, or not injective, or both, of course. And now let's draw our favorite diagram and recall quickly how we deal with both kinds of failure here. So when A is not surjective, then the image of A is just a proper subspace of Y. Let me draw it as some kind of plane. And it could happen, and it will usually happen, that your right-hand side B is not inside that plane, inside that subspace, image A. So maybe it's over here. Then the idea was to replace the right-hand side B here by the nearest possible point in the image of A, because these are the only points that you can reach as outputs of the operator A. And now let's suppose we are in Hilbert space. Then we can characterize this best approximation B tilde here via the approximation theorem by the fact that this line here is orthogonal to the subspace image A. So B tilde is the orthogonal projection down to image A applied to B. And now this new equation, AX equals B tilde, can be solved because B tilde is in the image. But if your operator is not injective, then that solution is not unique. Let's denote one of the possibly many solutions by x0. And we know that the set of all solutions of this inhomogeneous linear equation here is given by x0 plus the kernel of A, which is just the kernel of A translated onto the particular solution x0. And now out of these many solutions here, you want to pick the one that has smallest norm, so that is closest to 0, and you can kind of see that it must be over here. And you find this solution x at the point where the orthogonal complement of the kernel intersects your set of solutions. And another way to phrase this is you just say you take your particular solution x0 and project it orthogonally onto the orthogonal complement of the kernel. And so in the end we have 3 steps that bring us from B, the right hand side, to X, the solution. So the first step is this orthogonal projection here onto the image of A. Then the second step is solving that new and replaced equation AX equals B tilde. And the third step is, and again, another orthogonal projection now onto kernel A orthogonal complement. And if you take all of these 3 steps one after the other, you get the map that we denote by A plus, which is taking your right hand side of the original equation B and returns the solution X in the least squares sense. That is what we mean by AX tilde B. So let's write that last comment down explicitly. At first, your original right hand side B is projected down orthogonally to the image of A, giving you B tilde. From there, you're looking for a solution x0 that is turned into B tilde by applying the operator A. And then comes the orthogonal projection in X onto the orthogonal complement of the kernel, and that gives you the final solution X of your least squares problem. Each one of these 3 steps is linear, so that the composition that brings you from B to X is also linear. But that composition is nothing but the Moore-Penrose pseudo-inverse of A. Okay, so you could take this as an algorithm to compute the pseudo-inverse, but we will see better ones. But first, let's look at this alternative definition or characterization of the Moore-Penrose inverse. And this was a much more algebraic characterization, and it reads as follows. A plus is the only operator in the corresponding direction that is subject to the following conditions. ABA is A, BAB is B, AB is self-adjoint, and BA also. So yes, we've spoken about these 4 conditions in the very first week, but now we know a lot more maths, and maybe now we are able to actually understand why there is only one B subject to these 4 conditions, and why that must be exactly our operator that we already described. Okay, let's start. So suppose B is subject to these 4 conditions. Then from 1 or 2, you can conclude that ABAB equals AB, right? So you could get this from 1 by just multiplying B from the right, or you could get it from 2 by multiplying A from the left. Okay, but now 8 weeks later, we immediately recognize this as saying that the product AB is a projection. AB squared is AB. And because it's self-adjoint by condition 3, it is an orthogonal projection. Okay, so B is starting in Y, A is ending in Y, so this must be an operator from Y to Y. What is its image? So where is it projecting onto orthogonally? So let's try and find out the image of AB. Okay, so we're looking for this set. I've abbreviated it by U for first, on which we are projecting orthogonally, and that must be the image of AB, and that's why we make the following computation. The image of AB is contained in the image of A, because the image of A is the set of all outputs that A can produce if you allow arbitrary inputs, whereas here you feed A not with arbitrary inputs but only with inputs that B can output, right? Which of course limits this choice here and therefore possibly limits the outputs so that we have inclusion in this direction. By the very same argument, we can even multiply another operator from the right, making the image even smaller, possibly. And let's take A as this other operator, because we know something about ABA. By condition 1, ABA is just A. So we get the image of A here, and now if you read this from the beginning, you see that, well, obviously all these implications here must be equalities. And that's how you see that the image of AB is just the image of A. So the set U, which we are projecting onto, is the image of AB, is just the image of A, or in other words, AB is orthogonal projection onto the set U that is image of A. And of course that totally fits in with what we are drawing here. So the operator AB, well, B comes first, right, because we read from right to the left. So your operator B starts in Y at some point. Well, let's take B as a starting point because this is an arbitrary point here. And then B, which is the Moore-Penrose pseudo-inverse, takes you, we can see it here, to little x. And then from that little x you take A of x. Okay, but this x is on this set of all solutions that end up in B tilde. So AB takes you from B via x to B tilde. So of course, in the end, it's nothing but the orthogonal projection onto image of A. Okay. In the very same style, you check that B times A is a projection, and this time by number 4 it's an orthogonal projection. And with the same trick as in here, you see that the image of BA equals the image of B, so that BA is the orthogonal projection in X onto the image of B. And then you have to work a little more to see that the image of B is just the orthogonal complement of the kernel of A. And because orthogonal projections in Hilbert space are uniquely determined, it's clear up to here that B times A and A times B are uniquely determined by the conditions 1, 2, 3, 4, 5. No, actually there is no 5. And now it remains to show that from these two it follows that also B is uniquely determined. So suppose C is doing the same job. And then we can make the following conclusion. So B is just BAB by our second property. And now we start to exchange B's for C's, and we start here because AB equals AC by this condition here. Okay, and then you do the same here. So BA is just CA And if C is doing the same job as B, then it's also subject to condition 2 in place of B. So we must have equality to C here, but then you see that B and C must be the same, so indeed we have uniqueness of B. Okay, so I mean I didn't say it was trivial, but you can follow it line by line if you take your time, and then you will agree that this set of conditions here determines a unique operator B, so the only B that is subject to these 4 conditions, and then that is the starting point of A plus from this algebraic perspective. And we saw that because we know AB and BA are projections to certain subspaces that we can see here, well, it must be exactly the operator A plus that we have in mind here already. There is a third way to understand the Moore-Penrose pseudo-inverse, and that is connected to singular value decomposition. And this is the probably most important tool in chapter 4. So let's give it its own section.